Hello, everyone. Welcome to AstroFest. My name is Kevin Lewis. I'm with the Planets Foundation, and I am extremely excited today because we're talking to three very distinguished scientists from the SETI Institute. But before I introduce our guests, I'd like to point out that AstroFest is sponsored by the Planets Foundation. And if you go to lanatardy.com, you can find the full calendar of AstroFest events here on the calendar button. And these events and live streams give you the opportunity to learn from and ask questions to top scientists in their field. And it runs all the way to November 11th. So we have quite a few live streams set up over the next month. So at the same time, Planets Foundation also has a fundraising campaign for our technology and education initiatives. And we currently have one on Kickstarter. So if you click this Kickstarter campaign button, it will take you to the live Kickstarter page. And this is our most recent project. It's an adorable rhyming book for kids called Lana and Tardy Space Adventures that follows a young scientist named Lana and her adorable tardigrade friend named Tardy. Tardigrades are small little micro creatures that are found all over the Earth. And in our story, Tardy is giant because he comes from a super Earth. And if you scroll down below on the Kickstarter page, we actually have some real videos of tardigrades, so you can see how they move around and what they do. They basically just eat moss and algae all day. So let's get into the conversation. Move that over. There we go. So as I said earlier, today you're joining us for a very special live stream with the SETI Institute, and it's titled Becoming a Super Scientist. And yeah, let's introduce our three distinguished guests. So Janice, we can start with you. Senior scientist at the SETI Institute. Hello, Janice. Thanks for joining us.
Great to be here.
Yes, thanks for coming. And Dr. I should say Dr. Janice Bishop, if I didn't say that earlier. Dr. Kathryn Bywaters, research scientist at the SETI Institute. Thank you for joining us.
Hi, everyone.
And Professor Jill Tarter, Emeritus Chair of SETI Research Member Board of Trustees. Hi, Jill.
Hello there, Kevin.
Thank you for joining us. So, you know, this stream really is all about it's all about SETI Institute and what it's like to actually be a scientist at SETI Institute. So Janice, maybe we can start off with you. What does it mean to be a SETI scientist? What does that mean? And then also, what is the research that you actually do at SETI?
So my background is in chemistry and geology. And all of us at the SETI Institute are scientists passionate about understanding Earth and other planets and if life might have been possible. And each of us has a slightly different twist on the issues. So together, all of us address little bits of the questions, and that contributes to the whole. And so my part is remote sensing on Mars. And so we are trying to understand the surface rocks on Mars in order to find out if the planet could have been habitable. So here Kevin has a nice graphic, and this shows some of the orbiters across the top and some landers across the bottom that are on Mars. And one of the orbiters is called Mars Reconnaissance Orbiter, and that has a CRISM spectrometer that I'm working with. And there's some rovers across the bottom, and NASA just launched one this summer called Mars 2020, kind of a little boring name, but it will be arriving in a few months in February, and I'm sure we'll all hear about that in the news. And so the next graphic shows the MRO orbiter with the CRISM instrument, and CRISM sounds a little bit like prism, and the CRISM spectrometer uses light and measures the reflected light on the surface, and that tells us about the rocks. And so let's go to the next graphic as well. You've probably all heard about the electromagnetic spectrum and microwaves or X-rays, and the part of the electromagnetic spectrum we're working with is the visible part we can see with our own eyes, and also the infrared. So there are a whole bunch of wavelengths here, from teeny tiny to giant big ones. And so we're mostly using the ones we can see and the infrared. So let's go to the next page.
Awesome.
What I wanted to show you here, we're working with energies. So first I wanted to show you the energies that we see when your brain is telling you, I see something blue, it's processing the wavelength energy of that light that we get in. And so from about 400 to 500 nanometers on this scale is what your brain processes as blue, and similar for green and red. So your brain is processing that information and then telling you that looks blue or green or red. And so with remote sensing, then we're using a very sophisticated camera that has more than just the 3 channels that our own little spectrometer built into our brain can use. And instead it has a lot of channels. And then we use these to try to see the colors of the rocks and then process these in terms of the mineralogy on Mars, and then use the minerals to tell us if water might have been present and what kind of water. So let's take a look at the next slide. This shows what the CRISM spectrometer is telling us. So we see an image that's kind of like a camera. So when you take a picture with your camera, you see an image, and CRISM works the same way, except we see the rainbow of 544 channels. So for each little spot on the image, we're seeing this whole depth of channels, and we get these sort of wiggly lines that you see there, green and red and blue. And those are examples of some of the minerals that we're looking for. We're looking for clays and sulfates and other minerals on Mars. And so let's go to the next picture. The way we get this is the sun shines on a surface, and then the light is either absorbed by that surface, by the rock, or it's reflected. And so if it's reflected, then we catch it with our detector or with your own eyes up here when you're looking at something. And the material that is absorbed because the vibrations of the molecules are vibrating at the energy of that light. So let's go to the next slide. And what I wanted to show you is, in any kind of a molecule, like salt is NaCl, or more complex things like quartz or gypsum, have this distinct structure. And inside this structure, all little molecules are stretching or bending. And that vibration of their stretching and bending has a specific wavelength. It's kind of like if you're playing a guitar and you change the string length. So if you have a longer string or a shorter string, it has a different sound, a different pitch. And same thing with the piano. So we're doing the same thing, except we're not listening to it with the sound. Instead, we're looking at the energy of that wavelength. And so let's jump to the next picture. Here we go. So we're mapping these different kinds of colors on Mars in order to identify rocks that might have had water. And then we're looking for clays or sulfates. And some of these environments had hot water, and some had cold water, and some had salty water, or a low pH or a high pH. And so we use this data from the orbiter to pick sites on the planet that look really interesting and might have been habitable and might have had life and might have biosignatures, and then we send rovers there. So Perseverance is on its way and will be there soon. So Perseverance will be doing a few things, and one is geologic exploration, looking at the rocks to try to infer the history, and then looking for habitability and biosignatures. So using some of the instruments on board to try to characterize if those specific rocks might have supported an environment where microbes could have lived, and then finding a way to see if we can find a chemical signature or shapes of fossils to let us know that life was actually there. And it's also preparing to return samples. So part of the issue is that when we send rovers, the instruments have to be teeny tiny, small things in order to fit on the rover. So we can't send the best equipment that we have on Earth. So if Perseverance can capture some of these really awesome rocks and bring them back, then in the lab on Earth, we can look at these in more detail with a lot more powerful instruments.
Real quick, Janice, have we
Yeah.
ever brought back rocks from Mars? Is this the first time?
This is the first time. This will be the first time. So, and it's not going to be an immediate thing. So Perseverance is finding the best rocks and then putting them in a cache. And these are kind of like, you know, some of you might have water bottles that have an inside and an outside, and it keeps your water really cold all day on a hot day. So it's an insulated tiny little water bottle, and they fill it with rocks samples, and then it's going to sit there and wait for a few years until the caching system can come collect these and bring them back. So it'll come back soon. Yes. The next slide, I think, shows a nice little example of how that's going to work. Oh, it looks like it's not loading. There we go. Okay. So this is how the rover is going to go track around the surface, look for really awesome sites, and then prepare these samples in these caches. So leaving these caches on the blue spots on here, and then it'll come back. They'll be collected later. And another thing that the rover has that's kind of cool is the mini helicopter, and this is called Ingenuity. So Ingenuity is going to fly above the rover and have sort of a bird's eye view and look down and say, hey, Perseverance, over here, this is a really cool rock, so come over here. So it's the first time that we've tried having a helicopter to help navigate where the rover should go. So a lot of firsts on this, and we'll see where that goes. So the next step after we identify the most cool rocks that might have biosignatures is to actually identify those biosignatures.
Awesome. This is so cool. We have helicopters on Mars, and it's amazing. And I guess one quick question is talking about the ice caps on Mars. Is there ever, do you think we might ever send a mission to where the ice is on Mars? Or, no, it's kind of a random question. But.
Yeah, we might. Well, one of the things that when we send humans to Mars, they're going to need water. So current efforts are looking for where can we find water in the ice caps or other regions. But there's also concern with planetary protection. So some of the ice caps might be sites where life could exist. Most of Mars is pretty barren today. It's like a super cold and dry desert. And so we don't want to send rovers to contaminate these or send humans to contaminate these. But so in the future, that's going to be a big decision. You know, if you want to get ice to get water for the astronauts, if you go there, then you're probably going to contaminate them, because each of us is like a colony, you know, a million colonies of microbes. So,
right.
So whenever there's a human going anywhere, there's going to be contamination. But
awesome.
That's not a decision for today. That's a decision for the future.
Cool. Well, thank you so much. Super fascinating research. Your job seems incredible and very interesting. And then, yeah, I think we can move with Kathryn. So I'll pose the same question to you. What does it mean to be a SETI scientist for you, and what's some of the cool, interesting work and research that you do at SETI?
So being a SETI scientist to me means that I'm able to pursue my passion, and I'm able to go after interesting questions and really try and discover and come up with new questions. So it's really the questioning and the investigation that I absolutely love about being a SETI scientist. And we just heard from Janice about, the cool things that are happening on Mars or about to happen on Mars, and, looking for biosignatures. So I am an astrobiologist, meaning that I want to, hopefully find life somewhere in our solar system. I work primarily in our solar system, and we'll hear from Jill later about beyond that and what's happening there. And I think we have some slides that...
Yes, we do. Let me pull those out.
Great. So if you go to the next one, I don't know if you guys have really heard of astrobiology or what that means. So I just wanted to go over and put that into context a little bit. It really is looking at three fundamental questions, and that's how does life begin and evolve? How does life exist elsewhere, or does life exist elsewhere in the universe? And what is the future for life on Earth and beyond? So it all revolves around this focus of understanding life and how life kind of started. And we do that, if you go to the next slide. So we can do that by...
Sorry, did you say back to the next slide or the...
No, that was perfect.
Okay,
To the next
cool.
slide.
Sorry.
We do that by looking at life here on Earth. And we do that by looking at these really extreme environments. So we go to the coldest places, the driest places, the hottest places, and we investigate how life is able to make a living here on Earth in these really extreme conditions that might be representative of places on other planetary surfaces like Mars. And what we've learned is that life is really, really tough. It can survive in super extreme environments. Think of like really hot springs or really cold, polar regions. So it's really tough, and it's tenacious, which means it can survive for really long amounts of time. You have different bacteria that can kind of hibernate, if you will. They become spores, and they kind of go dormant and go to sleep for a while. So it's, they're able to overcome really harsh conditions. And when it gets too tough, they go into rocks. So rocks become happy little homes that protect microbes from these harsh environmental conditions. And then the last thing is, life is really diverse. Life will eat almost anything. So any mineral, organic compound, there's microbes that eat anything. They're kind of like, I wouldn't say garbage disposals, but they're not, they're very selective for the particular things that they eat, but you'll find a microbe that will practically eat anything. And then if you go to the next slide. All right, so we have different and I remember I said that we look on Earth at these extreme environments and kind of try to equate them to different environments on other planetary surfaces. So here we have Mars, which is really cold and dry. You also have these icy moons that have, a layer of ice on the outside, but a liquid ocean on the inside. And then you have Titan, which is really strange and not like anything here on Earth. So these are the different environments in our solar system. And if you go to the next slide. So when we talk about finding life on these planetary surfaces, we're not talking about finding little green men. So I just want to make that really clear. We're talking about, especially in our solar system, we're talking about finding microbes. So really, really small organisms that you can't see with the naked eye. And that's why biosignatures become so important. What you heard Janice talk about was these biosignatures are sort of the fingerprint of these microorganisms. And since you can't see them, it's really important to look for their signatures. Next slide. So just going over really quickly some of the constraints that we look at. We've talked about temperature. Water availability is huge. So one of the things when we look for life in our solar system, we look for environments that are within a temperature range that can have liquid water. And NASA forever has said, follow the water. And that's because we know that all life here on Earth has to have water to survive. And another thing that we have to think about is too much radiation. So, if you go out into the sun, you can get a sunburn, right? So the same thing can happen to microorganisms. They're much, much better at tolerating this, radiation than we are, but they still have their limits. So this is just a few of the things that we look at. Next slide. So my work, some of the work that I do is I go into these extreme environments. So, one of the things that I love is that I get paid to go play in the dirt, right? I get to get outside and get dirty, and I love lab work as well. So it's a good balance. But one of the driest places on Earth is the Atacama Desert in Chile. And here I've kind of pointed out Chile. It's in South America. And the sort of tan part that you see on the picture of the left is this big dried out basin. And that's a huge salt flat. So it's a really salty, really dry location. If you go to the next picture. So this is what it looks like. And as you can tell, there's no plants. I don't know if you guys, some of you might have been to Death Valley or to different really dry deserts, and you'll still see plants and stuff. Here you don't see anything. And you think that there's no way life could survive. But then when you break open these salt nodules, and you see the picture there, and you see that green line, right? So that's actually photosynthetic bacteria. That's bacteria that's using the sunlight for energy. And it's a community, and they're actually thriving. They're not just surviving. So even in these driest places on Earth, we still find life here. And that's just a picture of, I'm in the white suit. Since there is such little amount of life, any contamination from us will just swamp the biosignatures. So you have to be really, really careful when sampling.
I have a quick question, Kathryn.
Sure.
When you go there, like, what's that like? How long do you stay there? Can you talk just a little bit about your actual adventure going there?
Absolutely. So it's a really long plane ride. And it starts with months of preparation, because when you get there, you only have what you bring. You can't just run to the store, run back to the lab. So you have to be really, really prepared. So you pack everything, you make sure you know exactly what you're doing, and then you take a really long plane ride. And then you drive out into the desert, and we actually camped out here. So, you're camping in tents. There's nobody around for a while. And you're with your research team, which is really fun because it's an opportunity to spend time with your colleagues, and you're just out there exploring a new environment, and it's a lot of fun. You have dinner together since you're all camping out there. And it's a really good way to hear what your fellow scientists are doing and to work together. So I absolutely love it.
Yeah, sounds fun.
And another location, it looks a little bit like Mars, but this is actually Utah. And it's a site by the Mars Society, and they run simulations where you actually stay in that little white building you can see in the background, and you put on mock spacesuits, and you try and go out and do operations as if you were on Mars. And if you go to the next slide, so here you don't find life either. You don't see a lot of the trees and shrubs and grasses, but we find that life also exists here. In that picture down below on the bottom right, you see those dark grains, yes, running through that. That's actually a salt crystal. That's gypsum salt. And through that vein, you can't see it too terribly well, but that vein is actually a dark green. And again, you're seeing those bacteria live in the salt. And the reason for that is salt will pull water out of the atmosphere. So it makes this water available to organisms in really dry conditions. So we found that salt actually, provides a happy little home for organisms. And we learn these things by studying these extreme environments. I'm not quite sure how much time we have left, but this is just another site. This is a polar desert in the Canadian High Arctic, and I've gone there as well and spent 4 months actually on this island, looking at, as it warms up from winter to spring, what sort of organisms are able to stay dormant over the long, cold, dry winter. And when spring comes around, what pops back to life and how they're able to do that. So that's some of the field work that I do, exploring how these organisms are able to just persist in these really crazy environments.
So cool. Just like Janice, you have a really incredible job, so I'm a little jealous.
I love it.
And last but certainly not least is Professor Jill Tarter. Yeah, and I'll pose the same question to you. What does being a SETI scientist mean to you? And let's talk about some of the work that you've done as well.
Well, SETI stands for the Search for Extraterrestrial Intelligence. And so for me, the question is not just finding microbes, but could we find intelligent mathematicians out there somewhere beyond Earth? And that means that we've used telescopes, radio telescopes and optical telescopes, to look for signals coming from distant planets, and we now know there are more planets than there are stars in the galaxy, and we're trying to find in the electromagnetic spectrum that Janice talked about. We're trying to find signals that nature can't produce, but you need a technology to do. So we're trying to look for a radio signal that sort of shows up only on one channel of these billions of radio channels, or an optical flash that lasts only for 1 nanosecond, 1/1000th of a second. Nature doesn't do that, but lasers do. And we're also then looking for laser signals at one frequency that might be pushing some kind of solar sail to explore the interstellar distances between stars, or find out about other planets. So we use technology. We use technology that we've invented, that we know about, to look for evidence of someone else's technology. If you looked at Earth from a distance that's less than, say, 100 light years away, and a light year is the amount of distance that light travels in 1 year, so about 6 trillion miles. Well, we began emitting signals that look engineered about almost 100 years ago with early radio. And so if you were within 100 light years of the Earth, you might detect us. And that's what we're trying to do with signals from other exoplanets, planets orbiting other stars. And we now know, which we didn't when I was a student, we now know that there are many exoplanets. Every star has at least one planet. And as Kathryn and Janice were talking about, we also know about extremophiles, types of life that can live in environments that I was taught as a student would be totally impossible to have any kind of life. And so there's a reason to believe that there's lots of potentially habitable real estate out there beyond Earth. And now it becomes possible to ask whether any of it is actually inhabited by microbes who might modify the atmosphere of those planets in ways that would allow you to detect remotely these biosignatures, or inhabited by advanced technological civilizations, which could provide something that we call technosignatures. So it's kind of parallel to biosignatures, but it's evidence that life is there because of the modifying their environment with technology. So what might a technosignature look like? Well, I've already said it might be a radio signal, it might be an optical flash. But Kevin, if you can put up the first slide that I sent you.
Yeah.
So about 40 light years away from Earth is an amazing system of planets that we've discovered. Now, there are 7 approximately Earth-sized planets, and they're orbiting a very dim, small star, much smaller than our sun. And if you were to put this system into the solar system, all of those planets in their orbit would fit inside the orbit of Mercury. the nearest planet to our sun. And here you see an artist concept of what those planets might look like. Nobody's seen them. We know they're there because of how they tug on that little star at the center of the system. Nobody's seen them, but some artist has envisioned what these planets might look like. And because they're at different distances from the star, you would expect them to be at different temperatures. The planets closest to the star would be warmer. The planets farther out would be colder. And you would expect them to have different properties. But we're now building telescopes that are not just 10 meters across in the optical part of the spectrum, like the Keck telescopes on Hawaii, but we're beginning to build telescopes that are 40 meters across, and they have the ability to collect far fainter signals. They can see things that are farther away and smaller and dimmer. And so eventually we are going to build telescopes that are actually able to see these planets and not just have some artist conception of what they're like. But how might we know whether they're habitable? Well, we can look at their atmospheres. We can look for biosignatures. But we can also look for technosignatures. Just suppose that you're a civilization that has grown up on one of those planets and you're running out of real estate, right? You want some more room for your population. Well, you might decide to move to the planet that's nearest you and tweak it a little, transform it, so that it's more like the planet that you left. So what if, just imagine, what if when you grow up and are using these fantastic new astronomical telescopes, what if you looked at this TRAPPIST-1 system, and Kevin, can we have the next slide? And what you saw was that all the planets were the same. That shouldn't be, right? They should be different. But perhaps some advanced technological civilization has, in fact, managed to geoengineer all of these planets to give them lots more living space that has conditions that they enjoyed on their home planet. This could be a technosignature. And there could be a lot of other things that we will be able to discern with new telescopes that we're building on the surface of the Earth and in orbit that will look different than what we expected them to look like, knowing what we know about Earth and our solar system. And so it's these technosignatures that SETI scientists are looking for to find evidence of someone else's intelligence.
Great. So fascinating. I mean, that's one of the reasons I got involved with Planets Foundation is I think, you know, answering the question, are we alone in the universe, is one of the most important questions that we can possibly ever answer. So it's so great the work that all of you ladies do and, you know, what you've been able to build over the years. So thank you so much for explaining your jobs and your research and framing this great question for us. So we're right about halfway through, and I think we should turn it over to questions. We have a lot of questions from the audience, so let's hop into that. I'm just gonna post them on the screen in 1 second. So Braden asked 2 questions, and I'm gonna put that in there. So one of his questions is, what do you have to study in college to become an astronomer? And then also another follow-up question, is every scientist at the SETI Institute an astronomer? And
well, let me try and answer that question. What do you study in college? You study math, you study physics, you do study astronomy. If you want to be an astrobiologist, you probably add in chemistry and biology and geology to those other courses. And you basically try and understand the physical universe and what we know about it and how to use tools, how to use telescopes, how to use computers, and how to use or build detectors, such as Janice described, how something could be wandering around a planet in the solar system and measuring the properties of the rocks that are on that surface, or the kind of thing that Kathryn talked about. How do you find the evidence of life in these extreme environments? So, what was the second part of the question?
Is every scientist at the SETI Institute an astronomer?
No, we have all kinds of different scientists. That's one of the nice things about working at the SETI Institute. We have chemists, we have biologists, we have geologists, we have planetary scientists, we have astronomers, we have mathematicians, we have engineers, we have computer scientists. Each of these people has found something that they really love doing, and they've become really very good at it, better than anyone else probably. And then they look at using the skills they have learned and gotten good at, and they see how those skills can be used to answer questions about life on Earth or life beyond Earth.
I'd also like to add that it's not just scientists. There's also artists and writers that help convey these ideas and concepts to the public to help engage and inform and inspire. So
yeah,
there's a role for everybody.
You're right, Kathryn. We have an artist in residence program, which has been a lot of fun, and it helps us to understand what we don't yet understand, and helps us to visualize things.
I would also add that astrobiology and planetary science, these fields are a little more interdisciplinary than in the past. So in the past, thinking you either were going to study math or chemistry or physics or biology, and there was a little box and you would fit in that little box. And today with planetary science and astrobiology, there are so many different parameters. If you're studying astrobiology on Titan, you have to understand atmospheres and surfaces, and so there's a lot more to fit in the picture. So it's really helpful to be interdisciplinary, and you'll still in college need to have a main focus, but it's good to also think broadly and dabble and take a few different other science courses as well.
Yeah, sure, all really helpful. And one thing I was kind of wondering as all three of you were talking is, we know kind of what you need to study to become an astronomer or scientist, but were there any influences when you were younger that inspired you to become a scientist? Like for me, I'm more of like a business person. I always knew I wanted to be in business, but what inspired you guys to, or you ladies rather, to be scientists? Was there anything in particular?
I think I would say that I was always curious and asking questions and wanting to find out things. And some people who are scientists or engineers, they really wanted to build things to help people or make your life better. And those are all important in our society too. But I was always asking questions and trying to find out the unknown. So for me, that was how I ended up being a scientist.
For me, it was very distinctly my first cellular biology class. Learning about all the different things that happen within one cell seemed like a magical world that just, because you can't see it, but we know all these strange things happen. And it did. It seemed like magic to me. So I wanted to know how it worked.
Well, I understood that I wanted to be a scientist when someone told me that if you're a scientist, you never have to grow up. You never have to stop asking why. Why this? Why that? Why not something else? And I thought that was pretty amazing, right?
Yeah, exactly. Great. So I've got a few more questions. So how far can our radio telescopes see or hear? I think you might have touched on that, Jill, but how far can?
Well, if you're talking about the kind of leakage radiation that we put out in the radio, and probably the most numerous signals at the moment are our radio television stations, but they're not very powerful because they're trying to send a signal to the next county, not to the next star. You can't see those signals with the technology that we have any farther than the very nearest star, a few light years. But if you're talking about our more powerful transmitters, our radars, that we use to bounce signals off the moon and asteroids and other planetary bodies, you could see that kind of signal sort of halfway to the center of the galaxy. Right? So that's the kind of transmitters that we have. But we're talking about technological civilizations that are probably far older than we are, because if they're younger, they don't have any technology that we can detect. And so the most detectable technologies will be those that are older than us. And then you could postulate transmitters that are much more powerful. You can think about transmitters that would be able to use all of the power that falls on our planet to make a signal. And then there's the whole galaxy becomes observable for these massive transmitters.
So Jill, in our solar system, we have these NASA probes that are on Mars or Ceres or Europa or wherever, and each of these orbiters are sending their data back to Earth so that the scientists can see it, or the images and the data. Is that the kind of transmission that you're talking about, that we'd be able to measure if it were happening at TRAPPIST-1 or something?
Well, if you're talking about the data itself, unless you know how it has been encoded, how the information has been formatted, it's going to look like noise. But if it comes along with a carrier that helps the telescopes at the Deep Space Network find that message, it's the carrier that's so visible. That's the one channel on the radio dial, as opposed to the millions or billions that the data and information occupy. So it's really the carrier signal that we're looking for. Now, the really interesting opportunity for us is that for decades, we've asked a computer to look at radio or optical data and tell us if there's a particular pattern that can be found in frequency and in time. And that's the kind of signal we're looking for. But now we can build neural networks which can look at that same data in frequency and time and tell us not is there a particular pattern, but is there any pattern? Is there any indication that that signal is not noise, but has information content? And that will expand the kind of things that we can look for enormously. Of course, they have to be loud enough, strong enough for the neural network to find. But yes, it's opening up an entirely new window on the electromagnetic spectrum.
And then kind of a follow-up on that question, Braden again, he asks, has SETI found any proof of extraterrestrial life? And if so, what were they? And I might want to expand that a little bit to the WOW signal I've heard about. We thought it was a signal, but not. Maybe you can talk about, have we found any life through radio? And yeah, I'll just leave it at that.
Well, he asked if we found any evidence of life beyond Earth, and maybe we just did, right? Maybe by looking at the clouds of Venus and finding a gas that's called phosphine. It's phosphorus and 3 hydrogen atoms together. There's been a suggestion that that might indicate life living in the clouds of Venus. because when we find phosphine gas here on the Earth, it's always in association with biology. In fact, biology helps make that gas. And we've looked at Venus and we've thought of, we think, or there's a claim that we understand all the possible chemical networks, geochemistry and photochemistry, that could produce gas of produce this particular molecule in the clouds of Venus. And we can't find any way to get as much phosphine as is seen without maybe some biology being in there to help us along. And so this is a potential biosignature, but it's not unambiguous. Maybe we just haven't thought of all the chemical pathways that you could make this gas without biology. So maybe, Kevin, maybe we're about to understand that there's some biology beyond Earth in our solar system.
Maybe we're close. And I'll follow up with this is from an anonymous asker. Let me put this on the screen. So, why do you search for life on Mars? Why not other planets? And I think I'll expand that too. So, yeah, in our solar system, what are all the places that we think life could possibly be? Maybe we can go through some of those. That might be interesting.
So I think Jill hit on one of them, which is Venus and the clouds of Venus. And we do know that another interesting thing happening in the clouds of Venus is that they're absorbing more UV than we would expect them to. And one of the reasons why that's important is we know on Earth, one of the things that absorbs UV is pigment in bacteria. To help, protect them from that radiation. So there's been some interesting things happening in the clouds of Venus for some time. So that's definitely one of the locations. I think we look a lot at Mars because we know it was warmer and wetter in the past. It had, liquid water on the surface. But some of the new places that we're starting to look would be the icy moons or ocean moons. Such as Europa and Enceladus. So there's the rocky core of these moons. They're moons around Saturn and Jupiter. And there's a rocky core and then a liquid ocean and then a layer of ice. So this has been one of the locations, if you're following the water, that you might look for life. And then there's also Titan, which is a fun moon that has really strange chemistry. It has liquid lakes, but it's not water. It's ethane and methane. It's these hydrocarbon lakes. So within our solar system, there are quite a few places to look for life. Historically, we have looked mainly at Mars, only because we know that it's our closest. It's close to us. It was warmer and wetter. If life started, it could have started there. Maybe there's been planetary exchange we know there's planetary exchange between, Mars and Earth, and maybe some organisms got swapped. So there is that possibility. But there are definitely more places to look in our solar system.
Hey, Janice, is it possible that we're Martians?
There's a chance of that too. We do have meteorites, and Kevin asked earlier if we have samples from Mars yet, and meteorites are technically samples from Mars. They're rocks that were blasted off the surface and transferred around in orbit for a while and then hit the Earth. And so these meteorites have traveled from Mars to Earth, and it's possible that early life on Mars could have hitched a ride and transferred to Earth, and that might have spawned the life that we know on Earth. And one of the interesting things about the time that Mars was warm and wet and habitable was about the same time that life evolved on Earth. So we've seen fossils on Earth from about 3.5 billion years ago. That's sort of the oldest stuff we can see. And on Mars, the planet has been kind of dormant and dry and cold for the last 3.5 billion years. But before that time, it was a lot more interesting geochemically. And the challenge during the early time period for Mars and Earth was that there was a lot of stuff flying around in the solar system, and a lot of these impacts were landing, and they're producing heat and energy, which is a good thing, but they could also have destroyed life. So it's possible life might have evolved a few times on Earth and Mars and could have transferred back and forth. And what we have today is what survived. So,
so maybe.
Maybe. We don't know yet. We need to keep looking.
Yes. Another question. So is it possible to send radio messages back? And again, maybe to expand that a little bit. You know, imagine that there's civilizations living close to each other in different star systems. Would they still use radio to kind of get messages and data back and forth? And then how would we send messages if we wanted to? Would we just be using radio, or what would that look like?
Well, it's hard to string fiber between planets, right? Mm-hmm. So our transmissions are now going onto optical fibers, and our broadcast radio is diminishing. But if you're talking about interstellar distances, planet to planet, you need to send something that will traverse the interstellar medium. And if you're talking about really long distances, radio isn't absorbed or scattered the way light is. We've never seen the center of our galaxy at optical frequencies, visible light, but we've certainly mapped it in the radio. So that's one reason that radio would be a good choice, is because it travels without being very badly scattered or absorbed through the space between the stars, which we think of as being empty, but in fact it's filled with plasma and molecular clouds.
Gotcha. And then a couple more questions, because we're getting close to the end here. So I will post this here. This one is from Lourdes. She says, sorry, is that showing up? Yeah, perfect. She says, I'm an engineer. How can I participate and be a SETI scientist? And maybe if you can talk about, I know you have like a SETI at home program. How can people help SETI help your mission?
Well, certainly as an engineer, there's lots of devices, equipment, and detectors that Janice would like to have, and Kathryn would like to have, ways of observing on planetary surfaces or remotely on telescopes. Lots of devices that need to be built in order to do experiments that we can't yet do, as well as building radio telescopes and building back-end signal processing equipment that can search through the radio or optical part of the spectrum. We're actually trying in the optical to build a device called Laser SETI, which looks at all the sky, all the time, at optical wavelengths, so that we can catch a signal that is transient. It's only there for a little while. And you need to be looking everywhere if you're going to find it. So all these, there's lots of instrumentation to be built, but you have to learn how to be a good instrument builder, or you can be a software engineer. There's lots of code that we use that needs to get built to look at data in different ways, and particularly more and more and more massive amounts of data. We need to figure out how to build neural networks that can look at this stuff in ways that we haven't appreciated.
Great.
Yeah. That's true for looking at the planets too. Like with Mars, a couple decades ago, we were sending back, one picture a day, and it was really slow. And now the instruments are taking thousands of images and uploading them all and sending them all, and nobody can look at them as fast as they come. And so we're working more towards data mining and algorithms to assist us in finding something unusual or different in order to investigate that.
And one of the things I didn't talk about, but that I work on, is instrumentation development for life detection. So building instruments to go look for these biosignatures. And engineers, it couldn't be done without engineers. They play a critical role in developing, like we've said, this new technology. So engineers for sure play a part.
Great, yeah, for sure. All right, so I guess just a couple more questions. So we have a lot of younger audience watching the stream today that are aspiring astrophysicists and scientists. Is there any advice that you would give any young aspiring scientists, other than just obviously study hard and have a good math background? Like, what advice would you give to younger people wanting to be you three?
I would suggest go try new things. And we have an internship program for college students, really. But every time I have an intern, I tell them, you're going to learn something important this summer. You're going to find out either that you love what you're doing with me and this is what you really want to do, or you're going to find out, nope, that's not it. And so when you're going through taking classes and studying, that's one thing. But it's really different when you're actually being a scientist. So try to find opportunities where you can volunteer when you're a younger person and in school. Try to volunteer, or in college even. Maybe you can get a job or an internship and try out things that are totally different. So you may not know that you want to do something because you haven't tried it or you haven't heard of it. So open your mind and try a lot of things and find what you really like best, because if you're passionate about it and you love doing it, then you'll be much better than something you don't like doing.
Yeah, for sure.
I would also say reach out, like go through the SETI website or whatever university you might be thinking of. Or, if you see a program on TV and you're like, oh, I love what that person had to say, find their email address, send them an email, start a conversation. Not everyone will get back to you, but reaching out to these people, then when you're in the position for needing and looking for an internship, you have people you can contact and ask for opportunities. And it's just a great way to start a dialogue.
Yeah, great point.
Yeah, I think Janice is giving the same advice that I give, which is tell people to find something that they love and then work really hard and get better at it than anyone else.
Yeah.
And now you've got a skill that you can use to answer questions in all kinds of different arenas. And so then find the questions that are interesting to you.
Yeah, develop a passion based on curiosity and interests. So awesome. We are just about out of time. This has been so nice and wonderful. Thank you so much for joining us. I guess I'll just say that once again, you guys watched our AstroFest live stream with the SETI Institute, and we couldn't be more pleased and happy that you three were the ones that joined us today. So continue your work, you guys. Ladies, I keep on saying guys. You ladies are doing some amazing work, and we appreciate your time and energy. So hopefully we'll have you on at some point in the future. So until next time, we will see you all soon. I hope you have a good rest of your day.
Right. Thanks for setting
Thank you.
Thank you.
All right. Bye-bye.